Let's take a moment to look at a crate that we can use to help us parallelize our programs. Rayon is a lightweight data parallelizer crate that makes it super easy to convert sequential computations into parallel computations while guaranteeing safety from data races. A unique characteristic that Rayon provides is that it will automatically spawn our threads for us. But how does it know how many to spawn? Well, by default, Rayon uses the same number of threads as the number of logical CPUs available, assuming hyperthreading is enabled. Otherwise, it will just use the number of physical CPUs. So let's do a quick example of creating a program that computes the factorial of a number and compare the performance between single-threaded and multi-threaded. So the first thing we need to do in our cargo.toml file is add a couple of dependencies. And I've already added them. And so we need Rayon of version 1. And then obviously it'll take our latest version. And then also num and the latest version under 0.4. And then inside main we can start importing in these dependencies. So we'll go ahead and get them all imported in. So we'll start out with Rayon, prelude, and then asterisk to take everything in. And now we'll use num, and we want big unsigned int and 1. And then lastly we want standard, time, and instant. And this is going to be what we use to measure the time it takes for our functions to run. So we'll start off with creating our single-threaded factorial function, and it's going to accept one parameter of an unsigned 32-bit integer, and we're going to assign a big unsigned integer. And the reason we have to use a big unsigned integer is because if we used the largest unsigned integer that Rust provides us, which is a unsigned 128, our factorial would actually only be able to go up to 35. I found that out by just playing around with it a little bit. So we need to use a big unsigned integer. That way we can use much larger values when trying to compute our factorial. So when computing a factorial, we need to do a couple of checks. We need to check if the number passed in is equal to 0 or if it equals to 1. And if it does, then we want to return a big unsigned integer 1. Otherwise, now we can actually compute our factorial. And so we'll do from 1 to num, including our number. We want to map that value, that element, into a big unsigned integer. And then we want to call the reduce method on this, and I will explain to you what reduce is in a second. I just want to get this set up, that way we can look at it. And what do we have here? No function. Oh, could this need to be capitalized? There we go. Alright, so let's break down this code. So again, we created 1 to num, which is also inclusive since we have this equal sign, and then we map it into a big unsigned integer, and then we call the reduce function on it. And the reducing function is a closure with 2 arguments. So we have argument 1 here and argument 2 here. And argument 1 is going to be the accumulator, and then x is going to be the element that we're passing in from here. So what the accumulator is going to do is we're going to say, hey, take the accumulator and then multiply it by x. And then now that's our accumulator. And then just continuously do this until we equal num. And then reduce returns an option, so we have to unwrap it in order to get the value inside of it. So let's create a test program of this, or a simple test, just to make sure that it is working correctly. And the factorial of 3 is 6. So if this runs correctly, we should see 6, which is what we have printed out. So great. So we know that it's working correctly, but just to verify, let's also do 4, and we see 24. So awesome. So everything's working properly. So now let's take this function and let's use Rayon. That way we can have the code running in parallel. So we'll just call it multifact for multithreaded factorial. And our setup is going to be extremely similar. So we're going to take in an unsigned 32-bit integer, and now we're going to also return a big unsigned integer. So let's do our check again. Return 1, and then otherwise we want 1 to num inclusive. And now where Rayon comes in is we're going to call into par iter. And this is going to create an into iterator for us, but par stands for parallel. So we're going to create a parallel iterator. And now we're going to map big unit from, like we did above. And now we're going to call reduce again. And before I fill in what reduce is, let's look at the function signature up here. And we see that we have a, it disappeared, a mutable self and then f of type f. Well, if we look at this reduce function, we actually see the function signature is different. So we see that we're going to take 2 parameters in this case. So we need to modify it that way. And then this is going to allow us for parallel execution. So this reduce function actually comes inside the Rayon library. So let's set up this reduce function to allow it to be happy. So we're going to have a big unit of 1. We're going to have our accumulator. We're going to have our x value, the same as above, and then we're going to have accumulator times x. So what reduce is, and let's see if it gives us a good example here. So we have to include an identity parameter, which is what we're doing with big unit and then 1. And then the identity iterator is going to be where we start out at. So we'll have 1, and that's where our accumulator is going to start at. So it's just a different function signature provided to us by the Rayon crate to essentially do this up here. It's just typed out slightly different. And in this case, it's just going to return our item to us, so we do not have to unwrap this. So now let's look at this and make sure that our factorials are computing the same value. So we see 24 in both, and then just to make sure, let's do 3 again and make sure each one prints out 6. So great. So both of our factorial functions are printing out the correct values as we expect. So now let's create a benchmark for this. And this is where our time instant comes into play. So now we're going to create an instant and assign it now. And now we're going to calculate our factorial of 50,000. And now we want to print out how much time it takes for that computation. So we'll give it a little bit of styling. So we want it to print out 2 decimals into the second as seconds, or just 2 decimals. And we'll say now dot elapsed to get the time differentiation. So from time now to time now here as well. And then the difference between the two, so the time elapsed. And now we want to do this again, but we want to do it with our multifactorial. And so, if we run this now, the factorial of 50,000 single-threaded is going to take 4.92 seconds, and our parallelized factorial actually took 169.5 milliseconds. So that just shows you how much faster it is to run programs in a parallel manner. So if we run it again, and this time 40,000, we see that we're seeing magnitudes higher of performance speedups, which is why I wanted to show you just how awesome this Rayon crate is. So hopefully this was a very insightful lecture for you into the power that parallelizing our applications can provide for us.